gone. It's not coming back. But that's just the way it is. Okay, so I threw some homework out there. I mean, I didn't throw it, but it's there. Sunday, I'm making them all Sunday night. Okay, I'm just intrigued at this, so I have to, now that I've got my oh, wait a minute. Will it let me go? It might not. Because, okay, so I got to open the file, and I know I have it here somewhere, but I know I put it on Blackboard. So if you'll be patient with me, I just have to find out what I did last time is works. So let's see. This is still dynamics, for what I know. Go to content at the very bottom. There's that file. Your download started shortly, but then if you click it, does it just open it? No, but I think I can load it in now. Let's see. Open. Okay, can you open them locally? How did I do that last time?
Click on the file on the right side.
Over here? Okay. Well, I got two of them there. Last week. I guess it's the same one. Okay, so what I was doing the other day, so let's see if I can go back in here and find it. I threw all, oh, wait a minute. Oh, because yesterday, last Monday, everything went dead. So I started with this concept of that. This is just something weird. I had this idea, and I thought, well, let's try it out. So there's the matrix that we ended up with, and I can't zoom in on it. Let's see if I click it. I can't zoom in on it, but I still have it on my phone, so I can start MATLAB. And I just want to solve it and see if I get close to the same numbers, and then I'll go on and do what I was going to do for today. Hello. Okay. So it's there on Twitter, but instead of trying to read that little matrix, I'm going to read it off my phone, type it in. Let's see, photos. Okay, there it is. So the matrix has 1 over square root of 2. Let's see. 1 divided by square root of 2. And then minus 2 over square root of 29. And then the next row it says, now, it could be that I did something wrong, but I should have done this before class, but okay. Oop. What did I mistype? I don't see it. Let's see. Invalid oh, well, I should have hit a shift key right there. Okay. So there's the matrix. Then the right hand side is 7. 7 and minus 6. So inverse of k, I hope, k times the right hand side gives me, I get different answers. I'll go back into 17 and 19. I get 22 and 23. I'll go back and resolve that later. Maybe since there wasn't a lecture out there for this, I'll go back and do that in a lecture itself and then complete the problem. But let's go ahead into accelerations. So let's see. Oh, there we are. Content. Oh. And I may have to move that up out of the way to start writing on the board after I get there. Okay, so what I want to do is try to find a problem that has acceleration on it. So I think I'm going to have to go to the next. Okay, I'm right here. Instantaneous center. Okay, there's the accelerations. There's some examples. So in order to do this, I'm just going to go straight to a problem. And I want to try to find one that looks interesting, maybe has a... That's okay. Maybe I'll do that one, unless I find one that visually looks better. That one looked okay. I mean, he's got a lot of them, but I don't know that. Maybe I'll try that one. Get rid of this. And I think maybe I can roll it down and then get rid of this. So wait, this one, right? No, that's that one. That one. Okay, you know what? If I sort of stop it right there, I get a little bit so I can see. So first, let's do this. Oh, maybe I'll have to shrink it. Because half of it's off the... Okay. Let me do this real quick. Did I? Hang on. There we go. Oh, geez, they got this thing. Hang on. It's all... Okay. The way I did it a couple years ago is far better than this, but you do what you can. Okay, so here's the problem. And he gives you the velocity and then the acceleration. And actually, although there is not a link there, it is as if there is one, because it follows that path. In other words, this rocking back and forth, and it's 2 meters and it's an arc, so it's as if this is a link right there. So that being the case, that it's kind of like so, and there's a lot of problems that are like this. In this spot, that's labeled A, this is labeled B, so I'm going to label this point C. So since that's the case, and since he says that's going that way, I'm going to assume that this is going this way. Now, as it turns out, this has to go this way. So now, this velocity is on that link, and this velocity is on that same link. Even though this velocity is on this fake link, it's also on there. So with that in mind, I just draw perpendiculars to them and try to find where they're going to cross. And they don't ever cross. And because they don't ever cross, this is moving only in translation. Okay. Oh, how about just say only translating? Well, translation, it's okay. If it's only translating, omega B and A, or AB, should be equal to 0. Now that's from observation. Now, if I do it this way, velocity of A velocity of A relative to B plus the velocity of B, that is on link AB. Oops. AB. So that's on link AB. There's a pseudo link BC, so the velocity of B is equal to velocity of B relative to C plus velocity of C. This one's on link BC. So this could be thought of as a rigid link because the distance between B and C never changes as it moves back and forth. So you might as well in your mind just say there's a link there. He does this a lot. When he does these little slots like this that are circles, that's what's kind of happening there. You don't have to have them as a circle, but it actually makes things a lot simpler if you do. So this velocity is nothing. That velocity, he's kind of specifying as 4. Now this we observed. I'm going to basically go back and say, is my observation correct? And I think it is. But this should bear it out. So the first thing about this is, okay, and we need to basically set this as our approach. This is positive, that's positive, and rotation this way is positive. So I'll do this one down here, and I'll do this one like right here. So velocity of B is going to be, hang on, I, J, and K. Oh, let me do the one extra equation here. Velocity B is equal to omega BC, which is, I'm going to assume it to be rotating this way. Obviously, it's not, because this can't go this way if that's going that way. But I'm going to assume it that way, and it should tell me, no, you're negative. But this is the way I do things. I always assume things positive to fit the mathematical coordinates, and then I let it tell me. R, B to C, and there isn't a term to add right here, so that's kind of gone. Now I'll do this. I, J, K. I'm assuming it to be positive, just because I assume it always to be positive. The vector that originates at C and draws itself to B is pretty straightforward. It just goes straight up in the Y, and it goes a value of 2. And it's that. Now, I can do a cofactor expansion, but what you'll find out is, okay, just look at it. If I eliminate this and this, that times that times that. So look at the J, eliminate this one and this one. I got 2 zeros right here. I don't have any, but I better just be complete. Just to be on the safe side, eliminate this and this, I get 0, I get BC, 0, and 0. And I eliminate, go ahead and do K, but K never produces anything because it always has these two. You'll see you don't get the J component, and you only get an I. Did I copy that down right? I didn't. This should have been here, and this should have been there. Okay, so that times that minus that times that. Minus 2 omega BC. That times that minus that times that. Okay, so that's the velocity of B. Does that make sense? Yeah, because if this is rotating that way, this does go in the minus that direction. So I'm going to stick with that and let it tell me that it's wrong. And the way it tells me it's wrong is it switches signs on me. it will switch sides on me. So I've done one link, and that link is from here down. Unfortunately, I don't think I'm going to have room, so I'll take up this to the other side maybe and do it over there. And so if I take velocity of A, which actually is that 4, which actually I might as well just put it here. I'll do it this way, 4I. But it's also equal to, copying that over, omega AB, which we assume to be only in translation, but we need to go ahead and do this. AB cross R A up to B plus what's left there, and there's no particular reason I can't go ahead and put this in there, but I'm going to wait one more set. I, J, K. And now the vector. The vector that points to A, that's A, and it originates from B, kind of does like that. It's 2 meters, cosine this way, and it's what, 30? Yeah, 30. And 2 meters sine 30 and nothing. Now I'm going to go ahead, well, let me do one more step here. And then here, I'll go ahead and do this. I'll say omega AB equaling to 0, and I'll put a question mark. We'll answer that question in a second. I think we're okay with that. But take this down, put it right there. I guess I'll go ahead and put this in here. Minus 2 omega BC I. Now I'm going to carry these out. So I got this one because I knew its direction. I got this one because that link was connected both, that point was connected both here and on that link. It's shared. Now, 0 omega AB 2 sine of 30, sorry for my handwriting, minus J, and now 2 cosine 30, and then AB and nothing. Ooh, I'm losing space. I'm riding into the dark. Now, that times that, minus this times that, minus 2 sine 30 omega AB, which probably should have put that in front. And then this one, that times that, minus that times that, but I have a minus there, so it becomes a plus. 2, yeah, I'll do it this way. Cosine 30, J, minus into the dark, 4I. Now notice something that happens here. Okay, so the next thing you always do is you break away the I and break away the J. The J is the most interesting. Nothing, there's no J. And this, so all you get for the J is 0 is equal to 2 omega BC cosine. Okay. Why did I write BC? It's supposed to be AB. That's AB times that. Sorry. Cosine 30, and I don't have to put the J because I'm pulling the components of the J. Now if I pull the components of the I, we get a more interesting equation. And then there's more things on it. And then I jump over here. And so immediately you see the only way this can be solved is if that is the case. And then that makes that simple, because then omega BC, that's gone, because this is the same, this one and this one are the same. So you get this, and you get omega BC is equal to, okay, here, is equal to -2. So in fact, yes, it is going the other way. And what's interesting, notice something interesting about this. What's the velocity of B? If you knew that, omega BC. If you knew this was -2, that becomes -2 times a -2 becomes +4. So in fact, this is 4, and in fact that's 4. So this link at this instant is just going like that. It's not rotating, it's not spinning, it's just at this instant it's going like that. Now in an instant later it's going to be going like this and like that. But at this instant, going in translation directly to the right at a speed of 4. So in fact, what we saw on from our instant center is verified using these equations like this. Now, okay, now I should have read the problem to begin with. At the instant shown, the slider block A is moving to the right of the motion. Determine the angular acceleration of link AB, and the acceleration of point B. That would be this one. So I worked myself to that point. Now, here's what I had to have. I had to have, in order to go further, I have to have omega AB, which is just nothing. And then I have to have omega BC, which in fact, okay. I'm sorry. Omega BC is this one. It's going to the right. So I'm going to be meticulous and say it's 2. Okay, because it's okay. So positive is towards you. This one's going this way. It's going in negative. So I need to know these two. I mean, I could put a K here if you want, but I don't need it since it's not there. Now what I'm going to do is take this equation and put it over here and use that equation. Okay, so I got that. I'm going to do something interesting now. So I'm going to go from here. What I'm going to do is I'm going to copy this equation up here, and then I'm going to go down and do the equations from here. So I'm copying this. Velocity B is equal to omega BC. Now, technically, RBC plus, and, you know, now how do you get the accelerations out of here? Okay, so I don't need that. And technically that and this are the same thing. And the way you get the accelerations, okay, so I can just write it down, but, and then I'll explain. How about I do it that way? Acceleration of B is equal to omega BC, and you can see this in the book if you wanted to, but, sorry, alpha BC cross RBC. I'll come back and show how this came about, and we've done it before. Omega BC, the magnitude squared times R BC plus acceleration of C. Almost wrote B. Here's the thing. If you're looking to take a derivative, a time derivative of this term is just that term. That's all it is. If you take a time derivative of this term, it becomes that term, which actually looks really ugly. So let me fix it. I'll tell you what, I think I saw a green marker. Not that it really. So the green marker, you're dotting things and you get that. So how do you dot this to get that? And it was done in the book, but I'll just do it again. And that's this, okay? So if I were taking the time derivative of omega BC cross R BC, I would first take the time derivative of this, and then I would take the time derivative of the right term. So, so the first time derivative gives you this. The second time derivative gives you that. Okay. So let me do it without the subscripts. How about that? Well, now I might as well. Okay. So what you're wanting to do is this. So you take the time derivative of this one. So how about I do it this way? BC dot cross RBC. I'll focus on this a second and then say, well, that's nothing more than alpha BC. Hang on. So this term is that term. So now I got to dot this one. If I do that, hang on, BC crossed with R BC dot. Now, this one you stare at for a minute and you realize, okay, I'm trying to think of a way to explain this that's a little bit reasonable. It becomes, okay, it actually becomes, it becomes the velocity. How about I do it this way? It becomes the velocity of B relative to C. But the velocity of B relative to C, this became this. So in fact, it becomes omega BC crossed with omega BC crossed with RBC. Kind of weird. But mathematically, that term yielded you this. The same way this got built. In other words, this whole thing got built by this. RB, RB relative to C plus RC. You dotted this one, it became that. You dotted this one, it became that. You dotted this one and you're like, okay, wait a minute. Here's the thing about B and C. They are the same distance apart, B and C are. They aren't originally, they only rotate, so they become this term right here. And so likewise, we use that again, and we got this. Now in this book, now in other books, he'll do this. He'll say, we're just going to leave it like this. And this is what you're going to solve. This book, he recognizes that, let's look at this particular case. Here's C and here's B. So you draw from from C to B, you get this velocity. Now it turns out it's 4 to the right. But here's the thing. The actual omega is this way. So it's actually into the board. And now this is the velocity. This term is the velocity. And so I got a vector into the board. I got this. And I cross them. So I take the vector that's into the board, cross it with that one, and I get a term actually that, actually the omega should be crossed with this term. So the omega is crossed here. You kind of, it's hard to say, you move this up to here, or you move that vector down here. You take this vector, you cross it, and it's a vector that points this way, down towards this. So this becomes omega squared r, or v squared over r, something you've already seen. This is the centrifugal part. It turns out it always points from here back. So he decides, I'm just going to make that the scalar value. It always points not in the direction of r this way. It always points back towards the center of rotation, which is what he's doing. So in fact, this equation, which is just put in the book, and he does tell you a little bit about it, basically you can lead it through the example just like that. So the key is, how do we do that? Solve that, in other words. And it's not too terribly hard. You'll see why I left this on here from the last term. Okay. I left this on here because what we're about to see is something very similar. Okay, so here we're going to look at acceleration of b, which is that point right there, equals to alpha, which I do not know. I do not know this. I do know that, but I don't know this. But I can just write it down. And what's funny is, if you ever are at a loss of what to write, look here and copy it by just changing that. Copy that. And that is that term. So you have this that you can copy. Now, I didn't go back and do my check where I dotted the velocity with this last row. And I should have, but that would be this term times 0 plus 2 times the non-existent term. And I should have done that. I should have done that over here as well, and taking just this, which is the relative term, and dotted it with that row for a check. 2 sine 30 cosine 30 times omega b. 2 cosine 30 sine 30. Different sign. So in fact, the dot product zeroes out. So that was a check that I didn't do. Should have done. Now, omega bc. 2. And guess what? I just take 2. I can put a minus sign in there, but who cares? It doesn't matter whether this thing's going this way or this way. The acceleration, the centrifugal, it's still going this way. That's why that's a square. And then this vector. For me, if I just want to say, I'm tired, I don't want to think, I look and grab this row and write it. 0i plus 2j plus 0k. And that's what goes right there. That row goes right there. And then you got to put the acceleration of c. However, that's just 0. And so what's interesting is, if I want to cofactor expand this out, that's fine. Or I can just look down here and say I'll replace that with that. So that would be minus 2 alpha bc I. So why do a cofactor expansion again if I've already done it? And this matrix looks just like that one, or this determinant looks just like that one, except instead of omega, it's alpha. I already did it. I write it down. I'm done. So I don't have to think. Now I just take the 2, which is still minus. 2 times 2 is 4, and another is 8j. Now, what's funny, okay, stare at this for a minute. This points in the negative j. It's like this. It's 8. What's v squared over r? 16. Distance of 2 becomes 8. So in fact, that is the centrifugal component, that b going towards the center of rotation there. So now I got this. Here's why instant centers don't work in acceleration. The centrifugal part. If you look over here, if you look over here, I put it here. Okay, this is the velocity. So I put it. but I have now a negative 8 for the accelerations that gets tacked along. So because of that centrifugal part, it doesn't work. You know, as instant centers there, it doesn't work. So, so now what I've got to do is I've got to take this one, and then I got to go over here and do this, the accelerations in this term. Now I've got things really tightly bound here, but it's possible I could work this out. And I'm going to do it in an interesting way. First of all, he says that's 6. So what I'm going to do, this sounds weird, I'm just going to move back and put 6i, and I'm going to say that's the acceleration of this A equals to alpha AB crossed RAB plus, minus omega, instead of BC, it's AB, and guess what? This is really convenient because it doesn't exist. RAB plus the acceleration of B. Now here's what's funny. I'll take this term, I'll do this, 6. I'll take this, I'll do this, alpha. That's the same thing that was there before. And then this one was copied from here, but now guess what? Look at that. And I get this extra term, minus 8j. Now, this term just so happens that it's 0 because this is in translation. So that's the equation. So what's funny, I go through here, and alpha, this is the magic of the alpha B, C, I, minus 8j. And then, I no longer have this. I got 6. I have no idea who that is. Alpha, but I don't have time. But alpha, 2, and get alpha BC, minus 8j. Now, so I've just basically taken the velocity and erased it and rewrote it, but now, okay, what do I have left? Okay, so now I've got to make sure, I've sort of have to keep up with things. I have the J, and I have this 8. Okay, wait a minute. Alpha. This came from here. This was the new term. That got added, whereas it wouldn't have gotten added had we been in the velocities. Now, I got a 6 here. So I got 6. Okay, I 2 sine alpha, and then minus 2 alpha. Then I got no j component. I got this j component, and I got that j component. Now I've got a situation where, in fact, alpha AB is going to be equal to, okay, move the 8 over, divide by 2, so it's 4 over cosine of 30. And then I can take that, stick it in here, and actually put it in there to find alpha BC, but he never asked for it. He only asked for that. He also asked for the acceleration of point B, which actually I will have to have the alpha BC in order to find that. So I'll have to have alpha BC back from here. So if I take, oh gosh, this is a mess. So I'll take 6 plus 2 times sine of 30. Take the alpha AB, put back in here, times 4 divided by cosine 30. And divide all that. Wait a minute, I have 6. Move this over. So that means all of this has to be minus. And it has to be divisible by, or divided by 2. So there's my 2 terms. Once I get this BC, I can put it back in here, multiply 2 times it, and put that 8 with it, and that'll give me the acceleration. So in fact, this is the equation. There is no instant center for acceleration, number 1. The reason it causes a problem is because of the centrifugal term. When you get over here, it looked exactly like the velocity, except this centrifugal term got stuck in there. If, in fact, if this link wasn't in complete translation, it would be another complexity here. There would be the extra complexity associated with the vector. And so it would be even more complex. You'd get another term here, and you get another term here. That comes from that. But, in fact, this link is going translation to the right, so you're okay. So, I guess that's it in a nutshell. So, we'll work more of these, and then you'll have to work several of these for homework. And so since this is the part that I think is important in dynamics, I'm going to spend a little longer on this, and we'll work more and more problems. Some people go through this in a day or so, and then they're done. But I think that you've already seen, the 1/2 mv squared and all that stuff and the 1/2 kx, all that stuff from before. Those are simple problems, and they're important. But this is the new material that you're seeing here. So, so did you still have time to look at the registration stuff, or do you want to do the Zoom thing? What do you want to do? It's up to you.
I do have some questions, so probably set up the Zoom thing so we have time.
Oh, okay. Okay. So it's tomorrow. It pops up. The cool thing is it pops up on my phone.
Yeah.
And did it pop up on yours? Like if I go to Zoom, like right now, I have a count. Yeah, Reynolds at 10 o'clock, right?
Yeah.
It just popped up.
Okay.
So mine, once you fill out that thing, it just boom, and it just fills out my calendar. And I need things like that,
Yeah.
So yeah, we'll do that.
Okay. All right. Sweet.